Hello and welcome to our video lecture called Introduction to ERD Modeling. These are the learning outcomes for this lecture. After completing this video lecture, you should be able to explain what data modeling is. You should be able to explain why a good data model is necessary for an efficient, scalable, flexible, non-redundant database. You should also be able to explain the difference between data modeling in general and the specific approach to data modeling that we will be using in this class called ERD Modeling, or Entity Relationship Diagramming Method. This is the approach that we're using in this class, and also this is the approach to data modeling that is probably by far the most popular one in the industry. Also, you should be able to explain what entities are, why we create entities, what entities store, how entities are implemented at the database level. Also, you should be able to explain what attributes or fields are, how they capture various relevant characteristics of entities. Also, you should be able to explain why we use key attributes such as primary keys, foreign keys, why they're important for identification purposes and also for implementing relationships between or among entities. Also, you should be able to explain what relationships are, how those relationships are depicted visually on an ERD diagram, and how those relationships are implemented using primary and foreign keys. Also, you should have a good grasp on the concept of cardinalities. This is something that is used to quantify a relationship in terms of minimum and maximum number of links that a particular instance of an entity can have with instances in another entity. You should also have a very solid understanding of the Crowfoot Notation. This is the notation that we'll be using for creating our own ERD diagrams, and those notations they refer to how cardinalities are depicted on relationships lines. Also, you should have a practical understanding of how to use primary and foreign keys to implement or specify relationships at the database level or at the level of tables. You should also know what to do in case you have the so-called non-specific or many-to-many relationship on your diagram. You need to resolve it using an associative entity. So you should have a good theoretical understanding of what associative entities are and how they can be used to resolve a many-to-many relationship. Finally, you should have a good theoretical foundation for developing your own data models that would support a database, and you should be able to improve those data models by normalizing them. So those are the 11 learning outcomes that you should master after completing this video lecture. Okay, so let's start talking about data modeling. So what is data modeling? Data modeling is a technique for organizing and documenting a system's data. Sometimes it's called database modeling, but I would argue that data modeling is a more precise term because you're not really outlining any functionalities of a database, of a full-blown database management system when you're creating a data model. What you're doing, you're creating a layout or a blueprint of how data will be stored in your database, how it will be organized. And by doing that, of course, you're enabling a number of useful features and applications, for example, reports, queries, forms, and things like that. But it's not about modeling the database itself. It's largely about modeling the data, how it's organized, how it's stored. The specific data modeling approach or technique that we will use in this course is called Entity Relationship Diagrams, or ERD. It's a data model technique or approach utilizing several notations to depict data in terms of entities and their relationships described by that data. So as you can tell from this definition, the probably two keywords or two important components of ERD modeling or ERD approach to data modeling are entities and relationships. So those two concepts, entities and relationships, are at the heart of ERD modeling. And we will spend quite a bit of time talking about entities and relationships in this video lecture. So at the end, we are trying to create something like this. A very simple ERD model is depicted on this slide. So here we have four entities: dorm, student, major declaration, and major. Each entity has certain attributes. Some of those attributes are compound attributes. For example, dorm director is a compound attribute consisting of first name and last name. You can tell that from the dot notation. Also, you see that each entity has a primary key. Okay, it's marked as PK. And then some entities, the so-called child entities, the entities that are on the many side, what Yeah, here, for example. So student is a child entity of dorm. So this entity has a foreign key, which is a primary key that comes from the dorm entity. So this is how an ERD model, a simple ERD model, will look like. By the way, in this specific model, we are, as you can tell from the name of those entities, we're trying to keep track of students, their majors, and also the dorms where they live. So perhaps you're a president of a student-run organization on campus, and you want to keep track of students that attend your meetings and also where they live, just for scheduling purposes or for event planning purposes, okay? So another thing that I would like to emphasize here is that an ERD model is not a process model. It's not a flow chart. A lot of times people, when they see boxes and arrows or links like that, especially if they're familiar with flow charts, if they took a course related to programming, they think that this is some kind of flow chart which suggests there is some kind of time-framed process where you start here with dorms, you go here, then you go here, and then you go there, where it's not like that. It's not a process link, right? It's just a layout of your data, and those lines, they don't show like causality or flow. They basically show logical relationships between those entities or as they will be further implemented tables, right? So this is not a process model. This is more like a layout. You can think of it as a layout of your living room. For example, here you have a table. Let's say here you have a couch, here you have TV, and you use this couch to watch your TV, and then here you have, I don't know, an armchair, and here you have a potted flower, right? And you can see the potted flower from armchair. And so there are like those links between your furniture elements, but it's not about process, it's not about starting here, going there. It's just like the overall layout and the logical relationships, like your couch has that logical relationship to your TV because it's used for watching TV, right? So that's what we're talking about, a layout, a sketch of your data storage, and not any kind of process or specific application. Okay, so let's start with the first fundamental concept of ERD models, entities. So what is an entity? Entity is a class of persons, places, objects, events, or concepts about which we need to capture and store data. I'm not sure whether this sentence is grammatically correct, but I would say that an entity is something about which we need to store data. We need to store data about students, so we create an entity called student, for example. Let's use the following convention. Entities are typically named by a singular noun. So if you have an entity that will store information about students, meaning many students, you will use a singular noun, student, without s at the end, okay? And I think it makes sense, first of all, for the sake of consistency, where everybody uses the same grammatical form for naming entities. And it also makes sense from the perspective of this definition. Entity is like a category or a class, right? So it's like a single class, although it can have many instances. So student is a single class of people. So a student is a person who attends a college or a university, right? But it's a single class, like a single category. That's why singular probably makes sense. Although, once again, this student class or entity will store information about many instances, many students. An entity can be pretty much anything. An entity can store information about persons or people, like agency, contractor, customer, department, division, employee, instructor, student, supplier. Places such as sales region, building, room, branch office, campus. Physical objects such as book, machine, machine part, product, raw material. Entities can also be used to store information about events or processes such as graduation application. In a particular entity, will store all applications filled in by students for graduation, awards, cancellations, something in relation to flights, invoices, orders, and things like that. An entity can also store information about abstract, meaning non-physical, non-material concepts such as your bank account. If you think about the bank account as an abstract concept, nowadays, it has digital implementation. There are certain bits and digits that tell you how much money you have with that bank, and the bank knows how much money they can possibly give you, giving you account balance. But it's a concept, meaning it's your bank account is something that you cannot smell, you cannot touch it, right? You cannot throw it. Okay, it's like some kind of mental agreement that you have as a customer of the bank, and the bank has with you, right? And if you think about it, it's scary, because what if the bank says, "Oh, I don't remember any deposit that you have made," right? So you don't have like something like that you can take with you, right? Because it's not physical, right? So if they say it's gone, it's gone. That's it. There's nothing you can do. You cannot make something that doesn't exist your own again, right? If the other party does not share the same understanding that you have a bank account. So yeah, so once again, an entity can store information pretty much about anything that is relevant for business purposes. Now, one thing to keep in mind, always to keep in mind, and this will aid your understanding of a lot of further concepts such as primary keys, foreign keys, relationships, associative entities, normalization. So one thing to keep in mind is that once you create your data model, eventually every entity will be implemented as a table at the database level. So once again, when we're creating an ERD model, we're talking about a conceptual model for data storage, right? So then that conceptual model will be implemented in the form of a specific database management system, such as Microsoft Access. And each entity will become a table, right? So for example, here we have an entity called student. It stores information about students. You see attributes of that entity. And then the whole entity will become a table like that. So here this table stores information about 4 students, John, Jack, Betty, and Emily, okay? So those specific students or rows, they're instances or examples or real-world manifestations of that class or category that entity represents, right? And then columns are attributes of that entity. So you see student ID is the first attribute in the student entity. It's a primary key, so it's the first column here. Then you have a compound attribute called student name, okay? So I guess we can call it, it's a compound column that has 3 subfields: first name, middle initial, and last name, okay? So once again, entities are eventually implemented as tables at the database level. Each attribute becomes a field or a column, and each instance of that entity means each specific student about who we store data becomes a row in that table. So please keep that in mind when we discuss other more advanced concepts in relation to entities, that every entity is implemented as a table. So what is an attribute? Attribute, a descriptive property or characteristic of an entity relevant for business purposes. I would emphasize that last part. You see, an entity such as student can have all kinds of characteristics, right? We can have thousands of characteristics identified. However, we're not going to have an entity with 1,000 attributes. We're going to only capture attributes that are relevant for business purposes. Let's say relevant for the purpose of running a university or running a student organization, okay? So for example, a student, just like any person, may have a property such as height, weight, or hair color. Now, maybe a hospital will need such information about height and weight, but I don't think we need height and weight for the purpose of students' height and weight for the purposes of running a university, right? Maybe a barber shop will need information about hair color, but we don't really need it for running a student club. So that's why we only capture relevant property or characteristics with the help of attributes. Synonyms of attributes include element, property, and field. So I think in Microsoft Access database management system, they call attributes fields. We also mentioned that some attributes are compound. Compound means complex or comprised of other parts. So a compound attribute is an attribute that consists of other attributes. And synonyms include concatenated attribute, composite attribute, or data structure. That's the term that is quite often used in programming. An example of a compound attribute would be student name. The reason you see it's a compound attribute is because of that dot notation. You see that this attribute, student name, has 3 parts: first name, middle name, and last name. And those dots are used to show that those 3 parts belong to one single attribute called student name. And that student name is once again compound, concatenated, or composite attribute. So those are the synonyms that are used in relation to this category of attributes. An attribute can have a different data type. By data type, we mean the kind of data that it can store. So a data type is a property of an attribute that identifies what type of data can be possibly stored in that attribute. If you're familiar with programming, you understand why we need data types. If not, I will explain here briefly. We need data types, number one, first of all, to preserve memory. For example, if you have an attribute storing short numbers, short integers, you don't need to allocate extra space in memory for storing decimal point of that number, right? So you would use a simple integer as opposed to using a double, let's say for a person's weight in pounds, okay? So that will save some memory space. I think nowadays for modern computer information system, memory is becoming less and less of an issue, and the data type definition is more about keeping things correct and consistent. For example, if you specify that a person's weight in pounds is an integer, then if somebody wants to enter text, for example, use words like 200 pounds, the attribute will that situation will lead to an error because the data type for the weight attribute is integer and somebody's trying to enter text. So that has that limiting organizational purposes where you keep strict data definitions and you force users to adhere to those strict data definitions that you have. Some examples of data types in Microsoft Access. This list is not exhaustive. There are some other nuances and some other data attributes, but typical data types in a typical programming language or database management system include text for storing short words. Sometimes if it's a long text, like for example, customer review, they use something called memo. Integer for storing whole numbers like 1, 2, 3, 4, 5, and so forth. Double for storing numbers that have a decimal value, because once you have a decimal value, the number becomes longer, so you need to have more memory allocated for it. So that's why we use a different data type for storing decimals. Currency stores numbers representing dollars, cents, and other currencies. Yes or no or Boolean data type for variables that have only two values, such as 1 or 0, on and off, yes and no, true or false. And then date and time attribute for variables that store dates or times. Probably it's clear that we should not use an integer to store dates because dates have certain formatting. Also, dates and time values, they're not numbers. I mean, we use numbers to represent dates, but they're not numbers in the sense that you cannot perform arithmetic operations with them, you cannot multiply, you cannot divide them. So that's why you need to use a separate data type to format, to define a datetime attribute. Another thing worth mentioning is that an attribute can have a domain, which means a range of legal values that are allowed to be entered. For example, an attribute storing somebody's age may have a domain between 10 and 99. In other words, we expect the users will be between 10 and 99 years old. Another example of a domain would be like a possible format. For example, for date, the domain will be of this form. You will use a specific format for date and time. For yes or no variable, the domain can be yes or no, on and off, which means we cannot have values outside of that. And then we can have like a value set, let's say days of the week. We can have 7 values, and naturally we cannot have anything outside of that value set, right? We have 7 days of the week, so we cannot have users entering something outside of that set that we already have predefined. And also attributes can have default values, although nowadays it's not very common to specify default values for attributes. So what is a default value? It's the value that will be recorded if a value is not specified by the user. For example, let's say you have a database to store information about Murray State University students, and one attribute is called campus, which captures to which campus students belong to. Now, most students at Murray State attend the main campus, right? So by default, you can specify the value of this attribute as main campus. But you understand the dangers of using a default value. I mean, a lot of people, if you specify default value as main campus, let's say if they don't come from the main campus, let's say they come from Paducah campus or Hopkinsville campus, they will either not care enough to change it from the default value of main campus to Paducah, or they will simply forget about it, they will overlook it. So you will have a lot of bad data points if you use a default attribute. So I think nowadays it's a common practice not to include any default values for attributes. Okay, another important attribute in every entity is the so-called key attribute. Key attribute is an attribute or a group of attributes that assumes a unique value for each entity instance. So because a key attribute will assume a unique value for each entity instance, it's used for identification purposes. Okay. For example, in most universities, to uniquely identify students, they use an attribute called student ID. For example, at Murray State, that student ID, we call it M number, right? So we use M number, which is our student ID, to uniquely identify every student that has attended Murray State University. And there can be many candidate keys. For example, in a student entity, we may use a social security number as a unique identifier as well. And I remember there was a time in my university, University of Houston, where we used Social Security for student identification purposes. I think they quickly figured out that this is not a good idea because if you use somebody's Social Security for identifying that person as a student, then that information may leak and somebody will steal that Social Security number and then take out a loan on behalf of that student. So this is the so-called identity theft situation, right? So we can have several candidate key, but the primary key should probably be some kind of abstract student ID that is not linked to anything personal, such as a Social Security number. So the candidate key that is not selected to become a primary key is called alternate key. Another thing that needs to be mentioned is that in some entities, such as associative entities, primary keys are compound or composite keys, which means that consist of several parts, two or more parts. So that's what we call a compound key. But the most important concept here is the primary key. It's that unique identifier that is used for uniquely identifying each instance of that entity and also for linking entities together. Okay, so now we are done discussing entities. So that was the first key concept behind ERD modeling. Next, we're going to talk about relationships, which is the second most important concept in ERD modeling. So what is a relationship? It's a natural business association that exists between one or more entities. I would like to emphasize the following here. It's some kind of association between entities that is necessary for business purposes, that is necessary to be captured for business purposes. Because in this world, everything is related to everything, right? There are all kinds of relationships between objects, between people, but we only capture the ones that are relevant for business purposes. The relationship between or among entities may represent an event that links the entities or merely a logical affinity or association that exists between the entities. So what you see here in the simple ERD diagram, you see two entities, student and major. By student, we mean people attending a university. By majors, we mean fields of study such as accounting, finance, computer science, computer information systems, cybersecurity, and things like that. Okay. Now, think of it for a second. Do you think there is a relevant business relationship between students and majors? I would say there is, because students, they enroll or they choose majors, so that's the relationship going this way. And if you explain the relationship between majors and students going that way, you can say that majors are being studied or being populated or being selected by students. So this is the relationship. This is the relationship that exists between students and majors. And obviously this relationship is relevant for business purposes. It's relevant for running a university because we want to know who our students are and what kind of fields they major in. So this line represents a natural business association or relationship between students and majors. Now you see something at the ends of this line. This is something called cardinality. That cardinality quantifies, gives a number, attaches a number of relationship between majors and students and then students and majors. So we're going to talk about cardinalities in a minute. Another thing I would like to emphasize about relationships is that they are bidirectional. They're going both ways, right? I mean, by definition, a relationship has to go both ways, because if it's going only one way, right? For example, if you have a friend and the relationship is going from you to your friend, for example, you call that friend, you give that friend gifts, you invite that friend to see a movie, but there's nothing coming back from your friend, meaning he or she does not respond to your messages, does not respond to your invitations. So if it's not going the opposite direction, it means it's not a relationship. You don't have a friend, right? So here the relationship between entities is also bidirectional. It's going both ways, so it needs to be explained both ways, and it needs to be quantified both ways. So when you're going from majors to students, this is the cardinality, this is the quantification of the relationship. And when you're going in the opposite direction from students to majors, this is the cardinality quantification on this end of the relationship line. Now, I would like to mention that here we have a very simple relationship involving two entities. Relationships can be more complex than that. So here you have an example of an associative entity, and that associative entity links three entities together, not just two like in the previous example. The reason you know it's an associative entity is that it's created for the single purpose of linking those three entities together. And the other reason you know that this is an associative entity is because of its compound primary key. You see, assignment ID is the primary key of the assignment entity. It has three parts: project number, employee ID, and location number, which means that this assignment ID primary key is a compound or concatenated primary key. The other thing that you see is that project number, which is the first part of that assignment ID compound primary key, comes from the project entity. Employee ID part comes from the employee entity, is the primary key of the employee entity. And then the location number comes from this entity called location, right? So each record, each entry in that associative entity table links projects, employees, and location. And the name is good, assignment. Once you assign an employee to a particular project in a particular location, you create a row entry in that assignment entity. We will discuss associative entity in a bit more detail. So for now, I just want to introduce that idea of an associative entity that I already explained that an associative entity is created to link two or more entities together. Also, a bit later, I will explain how associative entities are used to resolve non-specific many-to-many relationships. I will show you how associative entities look at the table level, what kind of information goes into that table. But for now, I'll just use it as an example of relationship degree concept. So here we have the so-called ternary relationship, three entities participating in a relationship. So the concept of degree is, can be defined as the number of entities that participate in a particular relationship. A relationship between two entities is called binary relationship. So for example, this relationship is a binary relationship because it has only two entities. A relationship between three entities is called a ternary relationship, which means it's a relationship among three entities. A relationship between different instances of the same entity is called a recursive relationship. So we are talking about an entity being related to itself. An example of that would be an entity called class. We're talking about a class at a university. The reason it's related to itself is that some classes are prerequisites of other classes, so we need to capture that link. So that's an example of a recursive relationship where the entity that we call class is related to itself. Okay. Now let's talk about the concept of cardinality in a bit more detail. So cardinalities are depicted here on opposite ends of the relationship line, and the cardinality going from student to majors is here. It's on the opposite end, and the cardinality or quantification of the relationship between majors and students, meaning going that way, is on this end right here. Okay. So what is cardinality? Cardinality, I would like to say it again. It's something that quantifies the relationship, attaches a number of the relationship, but this is the expanded definition. Cardinality is the minimum and maximum number of occurrences of one entity that may be related to a single occurrence of the other entity. Simply speaking, this is what it means. Remember, each entity is implemented as a table. So let me show you those tables right here. So here we have two entities called students, right? And let's say we have another entity called major, right? Right here. So the student entity becomes a table like that, and the major entity becomes a table. So here we have several majors, computer information systems, computer science, CNM, and so forth. So here we have 4 students, okay? So this is what cardinality means. Let's say for now, we are going this way, from students to majors, okay? From students to majors this way. If we take a student from this table, we're talking about instances. If we select any student from this entity, what would be, in theory, the minimum number of instances in that major table that the student is related to? Okay. Well, in this case, based on the information that I see here, I would say that the minimum is 1. A student is associated at the minimum with one major, with one entry in this table, with one instance in this table, such as computer information systems. But remember, cardinality is also about maximum. So if you take any random student from here, what would be the maximum number of majors that student is associated with? Again, it depends on the university. Most universities allow double majors, triple majors, and things like that. And in ERD modeling, once it's more than one, you say many. So the minimum is one and the maximum is many, because one student can major in several fields, such as computer science and CS at the same time, right? So we identified the cardinality between students and majors, and it's depicted already here. A student is related at the minimum a student is related to one major. At the maximum, a student is related to many majors. Again, this is the art of system analysis and design. The specific cardinalities depend on the context. For example, somebody would argue that a student at Murray State can be may not have a major, so he or she has not declared major yet, so that's why it's zero. It's minimum zero, maximum many. Some people would say that, well, we can use non-declared major as a major category. We can add a record here in this table called non-declared, something like that, and that would be like still a major. So in that case, it's one. So it depends. I mean, it depends on the context. It depends on how you interpret the situation. So, a lot of times when you create a model, obviously a lot of things are subject to your own interpretation, to your own creativity, to your own approach to designing data models. So again, when you go from students to majors, at the minimum, a student will be related to one. So that stick means one major. At the maximum, many majors, right? So now we determined, we quantified the relationship between students and majors going that way. If we are going this way, from majors to students, then it looks something like this. If we take one major from this table, let's say CIS, what would be the minimum number of students that it's related to? Again, it depends on the context, on the specific university. I would say, like in a typical university, the minimum would be zero. Let's say it's a new major and no student has chosen that major yet. So the minimum is zero. And what is the maximum? The maximum, I would say, is many, because one major can have many students, right? So here we have only one student, John, majoring in CS, but obviously we can have many students in the table majoring in CS. Okay, so the minimum is zero, so the circle means zero. The maximum is many. So this Crowfoot, this notation means many. Okay, so this is how cardinalities are determined. Okay. Now, I already mentioned, that this sign here is called a crowfoot. So this is my drawing of a crow, of a bird. So they have feet like that. So that's why I wouldn't even say this is like an informal name. I think this is the formal name for this notation, crowfoot notation, because of that many sign. Okay. This crowfoot notation approach was popularized by Peter Chen for specifying cardinalities. You can read his original paper posted in Canvas. It was published somewhere in the 1970s, and you should be able to understand that paper based on the information that you receive in this video lecture. So now we will learn the specifics of that Crowfoot notation popularized by Peter Chen, and we'll use this simple table right here. It will only take a few minutes for you to get a hold of this Crowfoot notation used in ERD models. A stick or two sticks means one. The difference between one stick and two sticks is that this is like a strict one relationship. It means one and only one, right? Here's the difference between one and only one. For example, you have a table called dorm room, and you have a table called student, where you store information about students, and naturally here you store information about dorms. Let's say the kind of dorm that you're running is where each student has a separate little room, right? So in that case, at each point of time, a student is assigned to a particular room, and this room is assigned to only one student. So that's why it's only one stick, right? However, this relationship is not strict. It's not one and only one type of relationship, because students can be reassigned. For example, when a student graduates, he or she loses his or her room, and this room to assign to another student in the table, or a student may move to another room. Let's say he or she doesn't like to live on the first floor, it's too noisy, so they move to the top floor, so the room is reassigned. So although at any point of time it's a one-to-one relationship, that relationship can change, right? Now, if you're talking about storing information about students and their logins, it's a one and only one relationship, because not only at each point of time every student has one single login assigned to him. Those logins are not reassigned, they are not recycled. So for example, I've noticed like in some universities, like those faculty who have been there for like decades, sometimes they have this email such as John Smith, right? And that's their login ID. Now, as you can understand, if it's a big university over decades, there have been so many people named John Smith that went through the university, but they have that original login, and that login will not be reassigned, once they retire or move to another university, right? It's done for security purposes, right? You don't recycle logins between students, so it's one and only one, which means that it cannot be reassigned to another student. So I guess one way to explain it is that two sticks means a stricter form of one-to-one relationship. Okay, this circle in Crowfoot notation means 0. We already explained that, and stick means 1. So this cardinality means minimum 0, maximum 1. Here, this cardinality means minimum 1. So once again, the stick means 1. Maximum many. Once again, this Crowfoot means many. Here we have minimum 0, maximum many. And here we just have many, right? That's the Crowfoot itself, okay? So this is the Crowfoot notation that we'll be using for creating ERD diagrams. Now, we talked about entities and we talked about primary keys. So next we're going to talk about how relationships between or among entities are implemented at the table level, at the database level, at the technical level. A short answer is that you implement those relationships using foreign keys. A foreign key is a primary key of an entity that is used in another entity to identify instances of a relationship. So a foreign key is a primary key of one entity that is contributed to or duplicated in another entity to identify instances of a relationship. I know it sounds a bit complicated, but this is how it works. Let's say you have two entities and each entity has a primary key. So to show how instances in these two entities are related, you take primary key from entity and insert it into another entity, okay? And once you take primary key from one entity and insert it into another entity, this is how you show that instances are related. And once you do that, that primary key that is inserted into another entity becomes a foreign key, which means it's a key that is not there. A foreign key always matches the primary key in another entity. A foreign key may or may not be unique. Generally, it's not. It can be duplicated several times. The entity with the foreign key is called the child entity, and the entity with the matching primary key is called the parent entity. We're going to expand on this idea a bit more, but for now we'll just voice those definitions. So let me show you how those things look at the database level. So let's say we have two entities, one called student, so here we store information about students, and the other one is called dorm. This entity, this table stores information about dorms or dormitories on campus, okay? Now, let me ask you this. Do you think students and dorms are related? Well, the answer is yes, because students live in dorms and dorms are populated by students. So we have a natural business association between students and dorms that we want to capture, okay? Now, look, the student table has student ID as its primary key, while the dorm table has dorm name as its primary key. Now, typically you wouldn't use, let's say, a student name as a primary key because they can be duplicates, but I think it's okay to use dorm name as a primary key because I don't think there will be dorms with the same name on campus. Quite often dorms are named after people who financed the construction of that dorm. So here we have Jobs, Gates, Wozniak, and Musk. Those are the last names of people who financed the building of those dorms, and they use this primary keys. Now, we already said that students are related to dorms, right? So to show that relationship, we created an attribute in the student entity called dorm name. As you can see, that dorm name attribute corresponds to the name of the primary key here, right? So dorm name is the primary key in the dorm entity. However, it's a foreign key in the student entity because it's a foreign attribute. It's a foreign primary key. It doesn't come from here, okay? And also, student is a child entity, while dorm is a parent entity. We'll talk about this rule a bit later, how to distinguish between child and parent entity. But for now, we'll just say that primary keys from parent entities, such as jobs, so that's the primary key from the value of a primary key of the parent entity, is taken into the child entity and inserted here to show that John is related to the jobs dormitory, right? So this is how relationships are implemented at the table level. You take primary key from one table, in our case is dorm, and insert it as a foreign key in another table, right? In this way, we see how instances in one entity, which is student, are related to instances in the other entity, which is dorm, okay? So this is how it looks at the table level. Now, let's talk about some rules. We already mentioned that the way it works is that you take a primary key from the parent entity and insert it into the child entity as a foreign key. The question becomes, how do we know which entity in a relationship is a parent entity and which entity is a child entity? So this is the rule for you. In a one-to-many relationship where you have one on this side and many on this side, the parent is the entity on the one side, okay? And in the same relationship, one-to-many relationship, a child entity is on the many side. So once you figure out which entity is on the one side and many side, you know which entity is a parent entity, so that will be the one on the one side, and which entity will be the child entity, that will be on the many side. And the rule is that, and then the rule for implementing this relationship is this: you take the primary key from the parent entity and insert it as a foreign key into the child entity. So here's an example. We have two entities. We already discussed this example: student and dorm. As you can see, this is the one side, this is the many side. An entity on the one side is the parent entity, so dorm is the parent entity, and the entity on the many side is the student entity, so this is your child entity. To implement that relationship, you take the primary key, again, from the parent entity, which is dorm, and insert it as the foreign key into the child entity. So dorm name is the primary key of the parent entity. It's inserted here as a foreign key in the child entity. So this is how this relationship is implemented at the technical level, right? Now, the question is, what if both entities are on the many side? For example, one student can have many majors and one major can have many students, okay? So this rule does not seem to apply because we don't have one and many. In that case, we don't know which one is child entity and which one is parent entity. This is a situation that should be avoided. It's called non-specific relationship where many instances of an entity are associated with many instances of another entity. It's also called many-to-many relationship. So for now, I'll just say that this situation should be avoided. It's hard. There are some workarounds, but it's hard to implement a many-to-many relationship at the table level, at the database level. So one thing I'd like to say that you should not have a many-to-many relationship on your diagram, just like the sign suggests. If you do have a situation where a many-to-many or non-specific relationship arises on your ERD model, what you need to do, you need to resolve it by introducing an associative entity in between. And we're going to talk more about it in a second. So once again, to resolve a many-to-many relationship, you need to introduce an associative entity or table in between these two entities. So in our case, we have two entities in a non-specific many-to-many relationship: student and major. One student can be in zero or many majors, and one major can be populated by zero or many students. It's a many-to-many relationship, and we need to resolve it by introducing an associative entity in between. It's a bit hard to explain what an associative entity is because I think there's a lack of real-world analogies that would provide an example of what that entity is. So I can say a couple of things here to make that concept a bit more grounded in reality. Number one, it's an artificial entity. It's created for the whole, or table, it's created for the whole purpose of resolving a many-to-many relationship or linking two entities together. That's number one. And number two, the only real-world analogy that I can come up with for an associative entity is some kind of like a general ledger. If you took accounting, you probably know that general ledger is that big journal where all transactions are recorded, right? So whenever you, let's say you're running a store, like a small convenience grocery store, when somebody buys milk, you create an entry. Customer bought milk, 2 gallons of milk, the price is this, right? So, and then let's say your supplier brought, there was a transaction between you and your customer. Then there is a transaction between you and your supplier. Your supplier brought, let's say local farmer brought 100 gallons of milk to your store. So you create another entry in the general ledger, in the journal. I paid $200 for 100 gallons of milk, right? So like a general ledger is like a journal, and in the old days it was like a physical journal, like a book, like a big accounting book, where transactions between entities are recorded. So you can think of an associative entity as a general ledger. Whenever there is a transaction between a student and major, and the transaction is at the university involves a student declaring his or her major. So whenever there's a transaction, you make a record here. Student with ID 101 declared accounting with ID, let's say 102 as his major. So you create a record at that associative entity table. So that's the only analogy that I can provide to you to make this idea a bit more clear, I guess. Let me show you how this looks at the table level. So let's say here we have two tables, a student table and major table. In the student table, we store information about students, and then in the dorm table, we store information, in the major table, we store information about majors that students can select. I already showed you here that this is a many-to-many relationship, right? One student can have many majors, and one major can be populated by many students. So I told you that this is something that should be avoided because it's hard to implement that relationship at the table level. So for example, let's say a student with ID 101 declares CIS as his major. Okay, so we created we implemented this relationship using foreign keys, I guess, right? So that's fine for now. Now the question becomes, what if John declares computer science as his second major? What are we going to do? Some people may say well, let's have some workarounds. For example, we'll add CS as his second major. Now, this is not a good way of solving this issue because one cell should store only one value. So now we're making things a bit complicated and inefficient by storing two values in a single cell, right? This is not a good way of organizing data, right? Some people may say, okay, why don't we add another attribute called student major, and that will be student major 1 and student major 2, right? So when John declares computer science as his second major, we'll add CS here. Well, that may work to some extent, but the problem is this. You see, each time a student declares a major, what you'll be doing, you'll be violating the integrity of your database design. You'll be redesigning the entire table by adding additional attributes, right? So this is not a good approach as well, okay? So we're not going to do this either. You can also see I'm not going to provide this demonstration for the major table, but you can see the same thing. Let's say if you want to do it the other way, if we treat now major table as the child entity and we're going to insert primary keys from the student entity. So let's say John declares CIS as his major. So his ID is 101. So we add, let's say, student 1. And we add 101 to show that John is related to CIS major. Now, what if somebody else declares CS as his or her major? So we may want to create student 2 attribute and add ID 109 to show that another student has declared CIS as his or her major. So as you can see, this is not a good idea because each time a student declares his or her major, we'll have to redesign the entire table, right? So this is an example of why a many-to-many relationship should be resolved, why it will not work well at the database level. So instead of doing it this way, we're going to introduce an associative entity in between called major declaration. As you can see, this is an associative entity that has a compound primary key. It has two parts. Major declaration ID is the primary key of that major declaration associative entity, and it has two parts. Student ID, which comes from this entity, and major ID that comes from this major entity. So this is a compound attribute. And then you can add some supplementary information such as major declaration date to capture the date when a particular major was declared. Okay, so once again, the only thing I can say here is that major declaration associative entity is like a general ledger. It's like an accounting book where you create an entry each time a transaction between students and majors occurs. Okay, so this is how it looks. Remember, every entity becomes a table. So this is the table for the major declaration entity, and it's missing only one attribute, which is major name. Right, I just removed it. First of all, it doesn't belong there. Number two, this is just to keep this table clear. So this is how this associative entity table will look like. For example, John we're gonna delete that student major attribute from here. because it violates one of the normal forms, something that we're going to discuss later. And this is what we're going to do. If John comes to us and declares CIS as his major, we're going to create the following entry here. John has ID 101 and CIS has degree 01, right? So John, ID 101, declared major, which is CIS, with the code 01. Let's format it as a text so that it corresponds to the primary key of the major entity. So let's keep it as text. So John declares CIS as his major on, let's say, February 22nd, 2022, okay? Let's say John comes a year later and declares computer science with ID 01 as his major. So we're going to add the following entry, 02 on 20, 22, 2023, okay? So each time there's a transaction between a student and a major, we create an entry here. Then let's say Jack comes on February 22nd, 2022 and declares computer science as his major. So in that case, we're going to enter 102, 02, and the date will be the same, 10, 2, 22, 20, 22, too many twos, okay? And then let's say Betty comes to us, to the registrar, and declares CNM as her major. So her ID is 103, CNM has ID 03. So we're going to add the following entry here, 103, 03, and the date is the same. So you see, this is how many-to-many relationship is resolved. We create an associative entity, that captures all the transactions between those two entities, and we don't have to change the design of our table each time a student declares his or her major. So that's the whole point between using associative entities to resolve a many-to-many relationship. Okay, next we're going to talk about how one should go about discovering entities. By entity discovery, we mean identifying entities or tables that we'll have in our database. The most common way of identifying entities is through interviews. As a system analyst, you talk to users and you ask them about their work, and you take notes when they tell you about their work, about their data needs, and you keep track of those notes and you analyze those notes for the purposes of identifying certain nouns, right? So you scan those notes to identify certain nouns. For example, you go to the registrar and the registrar says, my job involves, keeping track of students and their majors. So you see two nouns, students and majors. So you understand that you need to store information about students. So you need a student entity, and you also need to store information about majors. So you need to have a major entity. Some interviews are simple one-on-one sessions where you meet with people, with users, end users. You ask them questions, you take notes. There are also the so-called scientific methodologies for conducting group interviews. One of them is JRP, Joint Requirements Planning. In a way, it's a complex methodology. It has many rules, many setup rules, how the group interview should be organized, how the notes should be captured. So some JRP sessions involve a certain layout for sitting, like there's a table. There are chairs where both technical and non-technical users are sitting, where IT personnel is also sitting. Then you have a scribe who takes notes. Then you have the GRP session facilitator, which is you, who asks questions. So there are many rules. I'm not going to go over those GRP rules, but I'll just say that naturally a group session can save time because you will interview all users at once instead of scheduling separate interviews with each of them. It will also help you build consensus because different users may have different opinions as to how information should be captured and stored. So this is your chance to resolve all those differences of opinion and come up with a consensus. Sometimes you discover entities by studying existing forms that people, paper forms that people fill in, existing files and reports. You scan them to see how people work, what kind of data storage needs that they have. There are automated tools as well where they can reverse engineer existing files and databases to identify entities. But even if you use an automated tool for entity discovery, there's no escape from the need of a human touch. A human still needs to look at those results generated by a computer-aided software engineering tool and fine-tune entities and attributes to create an efficient, scalable, and flexible data model. So this is how we discover entities. Those are the typical techniques that we use to identify what kind of entities or tables we need to have in our database. Now, the overall process for ERD model development is comprised of the following stages. You start with entity discovery. You identify the entities that you'll have in your model by interviewing people, reviewing documents, analyzing nodes. After that, you create a context data model. It includes only entities and their relationships. You just establish the entire scope, the project scope. So you'll see how large your data model is and how large your database will be. After that, you fine-tune the relationships by creating a key-based data model. You insert primary and foreign keys in all the entities. You add associative entities to resolve non-specific or many-to-many relationships. And you fine-tune your cardinalities to make sure they're precise. After that, you create a fully attributed data model, which means all our remaining relevant attributes are added. And then you normalize your data model. So that's step 5. You normalize your data model by going through the following normal forms. 3 normal forms. There are more than 3 normal forms, but in this class we're going to discuss only 3 because they're the most basic ones and the most useful ones in terms of making your model simple, non-redundant, and scalable, meaning flexible, adaptable for future needs. So let's see. So here's your entity discovery step. You just analyze nodes and you identify. And by the way, one thing I forgot to mention is that throughout this entire data model development process, you capture metadata, which means data about your data. You capture definitions, descriptions of your attributes, their data types to make sure that you don't get lost yourself during the modeling process, and also to make sure that somebody else can come in and learn something about your data model for the purpose of expanding or improving it. So that's why metadata needs to be captured at every phase of the model development process. So this is your entity discovery phase. You analyze nodes, you interview people, and you identify the following. You discover the following entities: student, major, and dorm. After that, you create a context data model. You just link those entities together to establish the scope, how large your data model is, and how large your final database will be. Then you create a key-based data model. So this is where you add primary and foreign keys to implement the relationships. Also, you fine-tune cardinalities based on that analysis. You make them more precise. And here you have a fully attributed data model. You add, in addition to having primary and foreign keys, you add all other relevant attributes that are relevant for your business purposes. So that's another phase of the data modeling process. And then after that, you create a normalized data model. Normalized means, simply speaking, improved data model. And this is something that we're going to talk about next. We're going to talk about normalizing data model. In the very beginning, on one of those first slides, I emphasized there was this bad keyword in parentheses. This model, we'll be using this model throughout this video lecture, but I would say this model is not as good as it should be. It's bad because it has several inefficiencies that we're going to eliminate through normalization. So the next topic that we're going to cover is data normalization or data model normalization. So by performing normalization, we are trying to make our model better. So what do we mean by a good data model? First of all, a good data model is simple. For example, data attributes that describe any given entity should describe only that entity. Each attribute of an entity instance can have only one value. So simplicity is something that is valued. Also, let me just explain this more. By simplicity, we mean like using attributes properly, without misplacing them, without creating any duplicates, without creating any situations where an attribute can have more than one value for a single instance, something like that. A good data model is non-redundant, so we don't have like duplications in attributes. We don't have an attribute recorded more than once under different names and different entities. And once your model is simple and non-redundant, it's also flexible and adaptable to future needs. It's easy to understand, modify, and improve something that is simple. If it's something that is very complex, that has a lot of redundancies and overlaps, it's hard to understand and improve or adapt for future needs. So data models are improved through the process called data analysis. It's a technique used to improve a data model for implementation as a database. The ultimate goal is to create a simple, non-redundant, flexible, and adaptable database. And the specific data analysis technique that we're going to look at is called normalization. It's a data analysis technique that organizes data into groups to form non-redundant, stable, flexible, and adaptive entities. What when we perform normalization, we'll put our ERD model into first, second, and third normal form. So there's an hierarchy here. If you're saying your model is in the second normal form, it's also assumed that it's in the first normal form as well, right? If you're saying that your model is in the third normal form, it is also assumed that your model is in the second and first normal form. Now, there are more than 3 normal forms. I mean, I remember reading about 7 normal forms. Each normal form definition is like a theorem from discrete math. There are some axioms and lemmas and proofs. But we're going to keep it simple. We're going to focus on the first 3 normal forms. Those are the most valuable ones for improving your data model. And we'll also keep it practical. We'll look at the definitions, but we're not going to have any proofs. We're just going to see like practical solutions and practical considerations. So for that example, we will use our student data model. This is the model that we've been using throughout this presentation. So it's right here. So we're going to put this model into the first normal form, then second normal form, and then third normal form. Okay. So let's talk about each of those normal forms one at a time. This is the definition of the first normal form. If you're saying that your entity or your model is in the first normal form, you're saying that you don't have entities whose attributes have more than one value for a single of that entity. In other words, in your model, in your data model, you don't have a situation where somebody will have to insert more than one value for a single attribute of an instance. Okay. I now already showed you with those tables, like where, let's say, if the model is not optimized, then somebody will try to insert, like for John, CIS and CS as his major. So that would be a violation of the first normal form. You have a situation where somebody wants to insert more than one value for the single attribute of a single instance. Okay. So take a look at this model, maybe pause this video and see whether you can see a violation of that first normal form. Okay. I think I already showed you one that is possible, but see if you can find anything else in this. Okay, so this is the first violation of the first normal form that I see. We have an attribute here called student major, and I already showed you at the table level that one student may have more than one major, and that will lead to a situation where somebody will try to insert more than one value into one single cell. So if you have a situation like that, it means that this attribute is not an attribute, it should be an entity. So you need to delete this attribute and create an entity called major to store different majors of students. And that led to a situation where we need to, it's a many-to-many relationship between students and majors. So we had to introduce an associative entity in between to resolve this many-to-many relationship as two one-to-many relationships, right? So we took care of that problem. There may be other violations of the first normal form. I would argue that this can be a violation major college, because remember, some majors are offered by more than one college. For example, CNM major is offered by the College of Engineering and also the College of Business. So somebody may have to insert 2 values for the major college. So that means that we need to delete it and we need to insert a new entity called college. Let me put it here. College, and let's say we're going to keep it simple. We're just going to have college name is the primary key. Now the problem here is that one major can be associated with many colleges, which means more than one, and one college can be associated with many majors. So we need to have an associative entity here in between called major college. Again, it's an associative entity used to resolve the so-called non-specific many-to-many relationship between majors and colleges. So the primary key will be major college ID. It's a compound primary key that will have 2 parts, major ID and college name, because this is how associative entities work. They link 2 entities through transactions. And then the second part will be college name, right? So that's the compound attribute. And then in that case, one major can be assigned to many colleges by creating, let's say, 2 transactions. However, each major college assignment is associated with exactly one major. So we're going to have I guess this one, because so each transaction is for exactly one major, right? However, one major, well, I guess it's one, right? It needs to be assigned to at least one college, so it's not zero many. Not this one. So you cannot have like a major without college, right? So there should be like one. And here we're going to have one or many colleges. So one college can have a zero or many majors declared. Let's say it's a new college, it can have a zero, but each declaration of a major should be associated with at least one college. So it's zero or many and one cardinality. Okay, where is it? And we'll straighten this line right here. Okay, so now we eliminated that first normal form violation by removing college attribute from the major entity, because college attribute can have more than one value for a single instance, for a single major, right? So now we can say that our model is in the first normal form. So let's go to the second normal form. If you are saying your entity is in the second normal form, you're saying that you don't have entities whose non-primary key attributes are dependent on the partial primary key. In other words, all non-primary key attributes are dependent on the full primary key. Okay, so first of all, here we're talking about compound primary keys. So we need to pay attention to entities with compound primary keys. So for example, here we have two entities with two associative entities, major declaration and major college. They have a compound primary key consisting of several parts. Okay, so second normal form means you make sure that you, in those kind of situations and those kind of entities that have a compound primary key, you don't have an attribute that is dependent only a portion of the primary key. Okay, it has to be dependent on the full primary key. Okay, now pause this video for a second and see whether you see any violations of this second normal form in either this entity or this entity. Okay, I see the following violation here. We have an attribute, non-primary key attribute here called major name. You see, to find out somebody's major, to find out the value of this attribute, major name, you don't need to have student ID, you just need to have major ID, okay? I know this example sounds a bit artificial, but let's say you're working as a database administrator for the registrar at the university, and somebody comes to you and says, like, what's the name of the major, right? They're asking you the following strange question: what's the name of the major? In order for you to answer this question, you will say, which major, which major ID are you talking about? Once somebody gives you major ID, let's say 101, that's CIS, you'll say the major name is CIS. So you only need major ID to get the value of this attribute. You don't need student ID. However, if somebody asks you, when did he declare his major? So basically you're interested in the value of this attribute. You need to ask two questions. You need to ask, who are you talking about? What's the student ID? So let's say the person says, well, the student ID is 101, which is John, right? So we're talking about this table, 101. Can you answer this question? What was the date when the major was declared? Well, not really, because there are two declarations. So you need to have student ID 101, and then you will say which major. And let's say the person says 01, which is CIS. Then you can say the major was declared on February 22nd, 2022, right? So I know it's a bit artificial, but hopefully what this example illustrates to you is that this attribute is dependent on the full primary key. In other words, you need to have both parts, student ID and major ID, to get this value. But this attribute is not dependent on the full primary key. It's only dependent on a portion of thereof, which is major ID. If that's the case, it means this attribute, which does not depend on the full primary key, does not belong here. You need to delete this attribute and put it where it's dependent on the full primary key, and that will be major entity, right? Once major name is here, and it's already here, it's dependent on the full primary key, which is major ID. I guess a simple way to explain what second normal form is, it means misplaced attributes. You eliminate misplaced attributes. You put attributes where they belong to. Once you do that, you make your model more organized and non-redundant, because here we had a duplication. Major name was here in this entity, major declaration, and also in the major entity. So we eliminated that situation, okay? Now, maybe there are some other violation of the second normal form, but I don't see like any attributes here, so probably not, okay? So that's the second normal form for you. And I think the third normal form is the easiest one to understand. If you're saying that your entity or your model is in the third normal form, then you are claiming that you don't have entities whose non-primary key attributes are dependent on other non-primary key attributes. This definition sounds a bit complex, and I try to phrase it in a reverse way. This is what third normal form is all about. It's about dependencies among attributes. Dependencies can be of two types. Arithmetic, one can be calculated from another. For example, let's say if somebody bought 2 apples at the price of $1, then you don't need to have a third attribute that is called order total, where you multiply 2 apples by $1 and you have $2. The reason you don't need to have it is that it can be deducted. If somebody wants to calculate, if somebody wants to develop an application that calculates order total, they will multiply apples, the number of apples, by their price to get that value. If this value can be calculated, you don't need to store it. That's redundant. Okay, so that's mathematical dependency. And then dependency can be a logical type. One attribute can be derived from another one. For example, all bachelors are male, right? If somebody is a bachelor, then you know that this person is also a male. So you don't need to store male for that bachelor person, right? So it's a logical dependency where the value of one attribute can be deducted from another one, right? So basically, if values of attributes can be deducted from another attributes in your model, it means those attributes are redundant. They should be eliminated. If somebody wants to perform those calculations, they will do it, but you don't need to have it in your data model, okay? Now let's go back to our student data model. Pause this video for a minute and see whether you can detect any violations of the third normal. Okay, here I see 2 violations of the third normal form in the student entity. First of all, you have an attribute called student age. Student age can be deducted from the student date of birth attribute. You just subtract date of birth from the current date to get student age, okay? Which means this is a redundant attribute. We don't need to store it. We delete it here. And think about it, kind of doesn't make sense. I mean, what, you're going to have a variable called student age, and what, at birthday you will update all the records for all the students, so once a year you will update those records. It's too much extra work that seems to be redundant. If somebody wants to calculate the current age of any student or a group of students, they can do it from the student date of birth variable, right? Another attribute, so this is more like a mathematical dependency. You can subtract dates, one date from another, to get current age. Now here it's an example of a logical dependency. You see, you have 2 attributes, student GPA and student academic standing. In most universities, good academic standing is defined as GPA of 2.0 or above. Once you drop below 2.0, you're in trouble, right? You're put on probation. There's that intervention team that tries to help you get out of the situation where your GPA dropped and things like that. Again, I would argue that student academic standing attribute or field is redundant, because once you know somebody's GPA, you know their academic standing, you can deduct it, right? So if you want to run a report that generates names of students that are in bad academic standing, you just use that student GPA variable. You list all the students whose GPA is below 2.0. You don't need to store information about their academic standing. And again, what if it changes, right? I mean, you have to update it again. So that attribute is redundant, right? It violates third normal form. It can be deducted from the student GPA, and that's why we eliminate it from our model, okay? So there may be some other violations. I mean, I'll leave it up to you, but I think I eliminated all violations of the first, second, and third normal form. And now we're done with that last phase of our model creation, which is normalization, creating a normalized data model, which also means creating a model that is good, meaning simple, non-redundant, and once it's simple and non-redundant, it's also flexible and adaptable to future needs. And that also completes our video lecture on ERD modeling. Thank you for listening.